Hi everyone, my name is Danjie and I'm from University of Guelph under the supervision of Professor Simon Yan. And today I'm going to talk about the review paper I'm gonna publish on this journal, whose title is Motion Planning and Tracking Control of Unmanned Underwater Vehicles, about their technologies, challenges, and prospects. We introduce the background. So because of the safety, autonomy, and flexibility of the unmanned underwater vehicles, which can also be abbreviated as UUV, the UUV has pulled the attention of scientists in recent years, and to realize its underwater operation, an efficient and robust UUV navigation has to be promised. And UUV motion planning and the UUV trajectory tracking control are the crucial parts that can help to realize efficient and robust UUV navigation. So for the UUV motion planning, in this paper, we mainly talk about the task assignment of the multi-UUV system, multiple UUVs chasing or say following the multiple targets, and the path planning of the UUV. And in figure 1, you can see the typical underwater motion planning scenario for the UUV, where the effect of ocean currents, underwater obstacles has to be involved, and also how to address the target area and finally reach the target are also topics that is covered by the UUV motion planning. And for the UUV trajectory tracking control, we divided them into conventional control, intelligent control for the trajectory tracking, and also the fault-tolerant control for the trajectory tracking under the cases when the UUV encounters the damage of its thrusters. Okay. First, let's talk about the task assignment problem for UUV motion planning. So here we divided the technologies used in this topic mainly in 3 categories. The first one is the behavior imitation algorithms, second one is agent-based algorithms, and also the intelligent algorithms derived by genetic algorithm or the neural network theory. And all the details of its mechanism, the logic, and the benefits and drawbacks can be found in our paper. Here we listed their benefits and drawbacks in the table. And in figure 2, it shows the structure of a self-organized map algorithm for the UUV task assignment, which is derived based on the neural network theory. The input are the target positions x, y, I, di in a 3D condition, and by retuning the weight wij, we can finally obtain the output of the optimal vehicle positions for the task assignment. So for the path planning of the UUV, it can be divided into one-to-one path planning from the vehicle position to the exact target position. And another one is called complete coverage path planning, which means the vehicle has to navigate all the area of the target place to finish the path planning. And here for the one-to-one path planning, you can see in figure 3 it shows a typical map building method, which is also one of the algorithms for one-to-one path planning, called the Voronoi diagrams for planning the path. In figure 4, it is the optimal path derived by the artificial potential field method. And in figure 5, it shows by inspired neural network based on neural network theory, and also belongs to the intelligent algorithms that can realize the one-to-one path planning for the UUV in underwater. So for the complete coverage path planning, here in the table we concluded them into a random strategy and sensor-based map building method, which is kind of similar to the map building method in the one-to-one path planning. Intelligent methods like based on genetic algorithm, neural network theory, and also a method called probabilistic priority based, which is derived based on a probability priority map. Okay, so here for the tracking control of the UUV, for the conventional control, the backstabbing control, sliding mode control, and monopredictive control are mainly used for the UUV trajectory tracking to realize its efficiency and robustness. And also nowadays we apply the intelligent controls as well, like based on the founding logic, neural network theory, and also genetic algorithm. So for the fault-tolerant control, in figure 6, you can see the typical structure of the UUV. Well, 6 degrees of freedom DOF are considered, but in most of the practical cases, only 4 degrees of freedom are involved, as the DOF of pitch and roll is usually supposed to be sustained at 0 to maintain stable movement of the UUV when diving underwater. So this gives us the opportunity of realizing the fault-tolerant control for the UUV based on the method called thruster control matrix reconfiguration, which is accomplished by the excessive number of thrusters than the number of degrees of freedom. So, for example, in the figure 7, the 2 typical UUVs all have 5 thrusters, 4 distributing around its body side and 1 in the center. You can see it's a cross section in the center. The 5 thrusters, the number of 5 is greater than the number of degrees of freedoms considered in the 2 UUVs navigation. So the thrusters can be able to retune the forces among them when encountering the damage of the different level of damage with the damage of different level of power loss, and finally sustain the UUV along the design trajectory. Okay. So finally, we talk about the challenges and prospects of the UUV motion planning and the tracking control. So the first one is the multi-UUV collaboration. Well, the environmental effect and the heterogeneous vehicles and also the dynamic targets can be involved in the future study of the UUV motion planning. The second one is called the efficient underwater positioning and path planning, which is also a crucial part for deciding an efficient UUV navigation. Third one is called robust underwater trajectory tracking, as the robustness is always an important problem in underwater navigation. The final one is called real-time underwater recognition. So the recognition of the UUV recognition of the surrounding environment, like the obstacles or the targets in the underwater situation, are also very significant for achieving efficiency and accuracy in the UUV navigation. Okay. So, video, and thanks so much for your time.